So today we're going to be covering the fourth section of Unit 8, and we're going to be covering the empirical rule. And the empirical rule is cool. So let's dive into this lesson. As we discussed during the last lesson, normal curves are symmetric, mound-shaped distributions. Normal curves are special as the mean and standard deviation provide a complete description of the distribution. So I'm going to highlight that because I think that's just important. And remember that in such distributions, the mean and median are approximately equal. When labeling a normal curve, it is important to note that the mean corresponds to the value under the peak of the curve. Okay, so the first exploration here is just matching, and we're going to match some information. It says match the means and standard deviations for the curves below. Remember mu, right, that looks like a cursive M. Mu is a Greek letter, represents the mean, and sigma, lowercase sigma, Greek letter, represents the standard deviation of the population. So it's just the mean, standard deviation, mean, standard deviation. Get the idea? Okay, so probably the first thing is, remember at the peak of the normal curve is the mean. And so if I were to go down here, right, this would be the mean, and so this would be mu, right, is equal to, it looks like 5. And let's do it on this one over here also. And so if I were to come down, oh, looks like mu here is 15. And then for this one, I'm going off to the side, see if I can correct a little. There we are. And then you can see here, mu is 4. And then here, mu is also 4. Well, 2 of these then we can identify quickly, right? Oh, you can't see it. You should tell me, sorry. So let's pull that up there so you can see. So 2 of them we could find really quickly because their averages are different from all the other ones, right? There is no other 5, there is no other 15. So it's going to be these 2 that we're going to have to do some thinking on. So the one that had the average of 5 is over here, 4. So 4 is going to be A. And then B will be the mu 15, that was 2. So now we're going to have to look at these graphs and figure out a couple of things about these graphs, like what distinguishes one from the other. And we're going to look at the bottom here. That's going to help me figure it out. Notice here that the range for this first one, right, looks like this is here about 0.5, right? This looks like it's about 7.5. So the range for this one looks like it's 7.5 minus 0.5, which is 7. So, and I'll just put a little approximately here. We're just close, right? Now for this other one, it looks like this looks like it's about, what, 2 right here. This looks like it's about 6 over here. And so if I'm looking for the range of this one, it would be 6 minus 2, which is 4. Okay, well, which one has the bigger range? C has the bigger range, 7, right? So I'll draw a line here. So this has the greater range, right? So therefore, right, Aren't we going to expect it to have the greater standard deviation? Right? If it has if it has the greater range, it's more spread out, and if it's more spread out, it's going to have the greater standard deviation, right? Because standard deviation helps us identify how spread out the data is. Would you guys agree with that statement? Okay. So when scaling the horizontal axis of a normal curve, we generally locate the mean and then count by the standard deviation. If asked to sketch and scale a curve, you'll usually go out 3 standard deviations in either direction from the mean. Okay, so are we? Oh, I didn't label the difference up here, did I? Okay, so if this one, they both have a mean of 4, those both have a mean of 4. This is standard deviation of 1. This is a standard deviation of 0.5. This is the greater standard deviation here, right? And so because this is the greater one, that would be C. And because this was the smaller one, D, this one will be D. Okay, are we good with that? Okay. I'm going to take that off. Let's go to the next page. The distribution of heights of adult American women can be considered to be approximately normal, with a mean of 64.5 inches and a standard deviation of 2.5 inches. Use this information to mark the normal curve below. Okay, so things that I know. I know that this is the peak, right? And the peak is going to be, this is the mean here, isn't it? So I'll call this 64.5 inches. So now we're going to mark out the standard deviations. So if I go out here, this is going out 1 standard deviation. That means I'm going to add 2.5 here. And if I go this way, I'm going to subtract 2.5, right? And so when I add 2.5 to 64.5, isn't that going to give me, oh, I have the wrong value down here. I'm adding 2.5 to 64.5. That's going to give me 67. Do you guys agree? Yeah? And if I subtract 2.5, won't that be 62? Okay, so I'm going to go here. So I'm trying to draw a nice line here. And a nice line here. And I'm purposely going above. Usually it's okay. And I'm going to just say this is 1 SD. This is 1 SD, right? 1 standard deviation, 1 standard deviation. Okay. And let's go out again, right? So this time I'm going to go out a second standard deviation. So I'm going to go over another 2.5, go over another, or subtract, right, down 2.5. So notice here, 62 minus 2.5, well 62 minus 2 is 60, subtracted another 5, isn't that 0.5? Isn't this 59.5? And if I add 2.5, isn't this 69.5? Am I doing my arithmetic correctly? Because it's not correct in my notes. Okay, so notice here, I'm just going to draw a nice tall one here, and this is 2 standard deviations. I'm going to do the same thing here. Make it nice and tall. This is 2 standard deviations. Okay, and then finally we're going to go out a third. Usually go out 3 standard deviations. So I'm going to add here another 2.5. So that brings me, is that 72? I'll go ahead and draw, well, I'll draw that in a second. And then going this way, oh, I meant to draw that. I'm going to subtract 2.5. Sorry, I meant to write that in blue, so I'm just going to do that to be consistent. Let's see, 59.5 minus 2.5 is 57. Okay, and then I'll draw in here. You can see almost all the information is within 3 standard deviations on a normal curve. Are we okay with that? Yeah? Okay. So what I'm going to do now, it says, so we've filled in, these values at the bottom. I've shown you how I came up with those values. This is going 1 standard deviation out in each direction from the mean, 2 standard deviations, and then 3. So now we need to learn, well, what is the actual empirical rule? That is the title of the lesson. And so the actual empirical rule is going to be what we have here. This is actually going to describe the empirical rule in this section. So the empirical rule, right, as mentioned, normal distributions are completely described by the mean and standard deviation. The empirical rule, or the 68, 95, 99.7 rule, reinforces this fact. This rule states that in a normal distribution, approximately 68, this first 68 here, right, represents 68% of the data is going to lie within 1 standard deviation, okay, of the mean, right? So going in both directions of the mean. So it's basically saying that going from right here to here, you will see 68% of the data. Does it look like that's about 2/3 of the curve? Right? Well, because of the height of the curve, yeah, right? Because remember, that's going to tell us how many. Are we good with that one? It also tells us, right, the rule states that then the second number here, the 95, okay, that's going to go here. So that 95% of the data lies within 2 standard deviations. Okay, so we can do that. And so going from right here to there, this is going to be 95% of the data. Okay, are we okay with that? Okay, and then finally, this 99.7 here is going to go down there. And so this is saying that approximately 99.7, let me just fix that here. .7% of the data lies within 3 standard deviations of the mean. And so I'll just draw going from here all the way across to here should be about 99.7% of my data. Okay. This is super powerful. It'll allow us to make predictions and things along those lines. Are we okay with that? Okay. I do want to show you, because this is actually helpful. Notice that if this is 68% going from here to here, right? Do you see that? Then notice that, right, this part of the data then going from here to here, and from here to here would split the 68. And so this would be 34% of the data here, and this would be 34% of the data there. Are we okay with that? And if going from orange to orange is 95% of the data, right? 95% of the data. Half of that would be, what, 47.5%, right? So going from here to here, wouldn't that be 47.5%? And then you would subtract the 34%. That means that 15% of the data is going to be from here to here. Does everyone understand where I got that number from? Yeah? I said 15. I lied. It's not 15. Couldn't be 15. It's 13.5. Let me fix that here. 13.5. I don't know where I got 15. So there you go. It's 13.5. So, and then notice to go from all the way here to here, that's 99.7%. We would divide that by 2, right? And that would give me going from here to here, right? Instead of going from here to here, half, right? Dividing it by 2. And then if you subtract the 34 and the 13.5, what you have left, right, will represent this section. And that's just 2.35% of the data is going to be found here. And here. Now notice, going 3 standard deviations isn't 100% of the data, it's 99.7, right? Well, that leaves 0.3, right, in each of those 3.3%, right, that is outside of 3 standard deviations. Okay, and so half of that would be 0.15, and so I'll just draw in my sections here, and this is going to be 0.15% here and here. Okay, so this is going to be really important, okay? These numbers down here as we continue in the lesson, but these numbers come from the 68, 95, 99.7 rule. Okay, so if you look at number 7 below, I'm not going to pull it up, it just says use the information to mark the curve, which is what we just did. Okay. All right, can we take that off? Go to the next page. This data, right, it's easily searchable, by the way, right, to look up the empirical rule, right, to get those percentages, 68, 95, 99.7. Okay, exploration 2. Right, it says here, estimate using the empirical rule. 500 freshmen of Schoenberg High School took an algebra test. The scores were distributed normally with a mean of 75 and a standard deviation of 7. Okay, so I'm going to use my data here. Let's mark in what we know. So I know going from the peak, right, it should come straight down. This is my average, which they tell me that the average is 75. There's my mean. And then the standard deviation is 7. So 75 plus 7, right, is going to be 82. And then 75 minus 7 is that 68. So I'm just going to mark that on my graph here. So this is one standard deviation in both directions. And if I go out another 7, 82 plus 7 is 89. 68 minus 7 is 61. Okay, and this is going to be going out 2 standard deviations. Same thing here. Let's go out 2 standard deviations. And then let's go out the third, right? 89 plus 7, that should be 96. 61 minus 7 should be 54. Okay, and then I'm just going to kind of about outside the curve, huh? There's my third standard deviation. Third standard deviation. Okay, now I actually kind of need these to go up a little higher, don't I? I'll just do this here. And just as a reminder, because it says label the horizontal axis, then use the empirical rule to mark the percentages on the distribution above. And so I am just extending those lines so that we can mark the percentages, right? It'll make it a little bit easier here. So I know that it's the 68, 95, 99.7 rule. And so I know that this is 68% of the data. It goes from here to here. I know that going from the second standard deviation, right, all the way across here is going to be the 95%. Okay, and I know that going from here, oh, I didn't go far enough, did I? It's from here, isn't it? Is going to be the 99.7%. Okay, so that's really, really helpful, but actually probably even more helpful would be to label what each of these regions are. And so I'm going to label this one way over here as 0.15%. This is going to be 2.35%. Actually, I should do the regions going here and here, right? And work my way in. 0.15. This is 2.35, right, with this one. And the next one is 13.5. 13.5. And then the last two are 34%. And those numbers, again, come from the numbers up above. Okay, it says label the horizontal axis, then use the empirical rule. So I've done that, check. What percentage scores are between 61 and 82? So we're asked to go from here to here. So if I'm going from 61 to 82, wouldn't it be the 13.5, the 34, and the 34? Okay, and I'll just tell you, when you add those together, you're going to get 81.5%. What percent of the scores are between 75 and 82? Well, that's just going to be the 34%, isn't it? There's nothing to do there. What percent of the scores are between 61 and 89? Here's 61, here's 89. Wait, isn't that or two standard deviations out? So I could add 13.5 plus 34 plus 34 plus 13.5, but we also know it's 95 because it goes one standard deviation. So I'm going to use that data and just write that here. What percent of scores are less than 61? Well, here's 61, so it's the 0.15% and the 2.35%. So I'll add those together. So it will be the 0.15% plus this one here, 2.35%. And when I add those together, I get 2.5%. What percentage of scores are greater than 96? Well, greater than 96, it's just that. It's the 0.15%. Okay, now it's switching just a little. Now it says, instead of asking for the percent, it says how many students, right? How many algebra students scored between a 61 and an 89? Wait, didn't we already find the percent here that was 61 to 89? Do you see that? So I'm going to take this number here, I'm going to change that to a decimal, 0.95. That represents the 95%. And then how many students were there? Well, if we look back up here, there were 500 freshmen. So this is going to be times the 500 freshmen. I'll write it out for this one. Well, I just have to multiply those together. 0.95 times 500. I'll tell you that's 475 freshmen. Or students. Okay, are we okay with that? I'm going to zoom out for another portion of this. Let me focus that. Okay, so because I need the curve and I need to answer still 4 more questions. Approximately how many algebra students scored between 68 and 82? Well, here's 68. Here's 82. Oh, that's just one standard deviation, isn't it? So I know that that's 0.6a, right? So I'll write that here, 68%. So I'm going to take that 0.68 and I'm going to multiply it by the 500 freshmen. I'm not going to write it out this time. 0.68 times 500 will give me 340 freshmen or students. I'll write students this time. Are we okay? Approximately how many algebra students scored between 61 and 75? Well, here's 61, here's 75. Oh, we're going to have to do a little bit of work here. So that's going to be 13.5 plus the 34. So I'll put some work here. 13.5, right, percent plus the 34%, and I get 47.5%. So now I'm going to take that number here, I'm going to write it as a decimal, 0.475, and I'm going to multiply it by the number of students, the 500. And when I multiply those, you get 237.5, right, students. Can you have half of a student? No. I noticed, though, that in this curriculum, they're okay with leaving it with the 0.5. But, you know, if we're going to actually make a prediction, we would either say 237 or 238, depending on what we want to do. If we want to truncate and just say, well, you can't have half a student, so it's 237, or if you want to round up, okay, because we're making predictions. Okay, I'm going to bump this up just for the last two. I just need the numbers down below anyways right now. And so it says here, approximately how many algebra students scored between 89 and 96? So here's 89, here's 96. It's that 2.35%. Okay, so it's the 2.35% is all that's in there. As a decimal, that's 0.0235, and we're going to multiply that by the 500 students. And when you do that, you get 11.75 students. And again, you can't have 0.75 of a student. Some teachers will just say you just truncate, take off the decimal and say 11. Others will say, oh, we're making a prediction so we can go to 12. Okay? Approximately how many algebra students scored higher than 89? Okay, well, 89 is here. That's the 0.235 plus the 15.15%. So it's 2. I got to do a little bit of work here. So 2. Oh, almost wrote it wrong. 35 plus the 0.15. And so when I add those, I get 2.5%. So, and then when I apply that here, it's going to be 0.025 times the 500. And when you multiply those, you'll get 12.5. Again, you'll either truncate it and say 12 students or round up to say 13. Okay, any questions on that page? Okay. Anyone still copying this down? Okay, let's go to the next page. Practice, okay, so over the hill. So aging on a normal curve. It says here, we are going to apply what we learned to curves constructed based on U.S. Census data. For each problem, use the curve and use the curve and the given mean and standard deviation to answer the questions. So you can see we have this data right here, right? Number of counties is here. Percentage of seniors age 65 and over. And it says the histogram to the left displays the proportion of people 65 and older in counties across the U.S. The mean and standard deviation are, and then so you can see it says mu is 0.18 and sigma is 0.04, right? That's the mean, that's the standard deviation. Use the histogram, since the histogram looks approximately normal, right? Because we see the mound shape, we see that it's symmetrical, right? So it's good. we are going to approximate the distribution to a normal curve. So I'm going to go ahead. It says fill in the normal curve using the empirical rule and the given mean and standard deviation. So here, right, we know the peak is going to come straight down here. We know that this is going to be mu, which is the 0.18. I'll write it as mu here. I'm okay if you write x bar, but since they use mu, I'll do that. And then we're just going to add 0.4 going off in this direction. And so 0.18 plus 0.04, that gives me 0.22. Add 0.4 to that, that's 0.26. Add 0.4 to that is 0.3. Going the other direction, subtracting the 0.04, that gives me 0.14. Subtracting 0.4 from that, that's 0.1. And then subtracting 0.4 from that is 0.06. Okay, and I'm just going to going to draw these lines in here just to remind myself, right, how the data falls. Okay, and I'll remind myself, I know this is 34% and 34%. I know the next one out is 13.5%. Then I know it's 2.35. And then it's 0.15%. Okay, so I'm going to bump this up here quite a bit. So that's 13, 14. Use the empirical rule to answer the questions below. So in approximately what percentage of the counties would the proportion of people 65 and older be more than 22%? So we're looking here for, right, be more than, that should be a then there, more than 0.22. Okay. More than 0.22. Here's 0.22. So we're literally looking at just these last three. Okay, so that would be, so it'd be the 13.5 plus the 2.35 plus the 0.15%. And when you add those together, I'm just going to tell you that's 16%. The next one says, in about what percentage of the counties would the proportion of people 65 and older be less than 0.14? Well, isn't it these bottom three right here? So notice in that case, right, that would be the 0.15 plus the 2.35. Notice I'm leaving out the percents now, but you know their percents. 13.5, add those together, you get also 16%. And then finally, it says, in about what percentage of the counties would the proportion of people 65 or older be less than 0.1? So here, we're talking about these ones, right? So that's going to be the 0.15 plus the 2.35, which is 2.5%. It says, according to the actual census data, the actual percentages were the following. So notice here it says that I'm going to use the same highlight in the same color. 12.6 of the counties had a proportion greater than 0.22. Okay. Does that seem to match up with the 16% here? If I compare those? There's a little bit of a distance there, huh? Right? Well, let's take a look at the other two. It says 16.5% of the counties had a proportion less than 0.14. So that's this right here. Okay, so now we're comparing the 16% here and the 16.5. That's actually looking better, huh? That's actually close. I would consider those about the same, huh? Okay, and then finally, you can see here, it says that 2.2% of the counties have a population, had a proportion less than 0.1. Well, we had 2.5 and they had 2.2. That's actually really close, isn't it? So it says, compared to the percentages that you just calculated in AC, does the actual data support the use of a normal model for this distribution, and explain? So let's just put this down. I'm going to say the second and the third percentages are really close. The second and third percentages are really close. The first is a bit off. Not crazy off, but it's enough of a distance that it's like, right? We're not like, nah, that's not like the totally matches. Okay. So, but let's keep moving here. And what I would say is that no distribution is perfectly normal. So therefore, I think it is close enough to support a normal model for distribution. Okay, I think it is close enough to support a normal model for distribution. Is that clear? Okay, I'm going to bump that up just enough, right? Just to have just that. And then the lesson summary, you can see here it just says the empirical rule is a useful tool for making predictions and estimates for distributions that are approximately normal. According to the empirical rule, in a normal distribution, approximately 68% of the data will lie in one standard deviation of the mean, 95% of the data will lie within 2 standard deviations of the mean, and 99.7% of the data will lie within 3 standard deviations of the mean. The empirical rule is another useful tool for in helping us helping us determine whether a normal model is appropriate for a given distribution. And then you can see here, they actually give us the percentages along the bottom that would break up for each section. Is that clear? Okay. So with that, it will wrap up my lesson.